I would first like to begin with a quick outline of this presentation. So first up, I'd like to begin with the introduction where I talk about the goals of our project, then pivot to the software and hardware frameworks which made it possible, then spend a little bit more time on the actual engine control application, and then we'll finish off with the results and conclusions. So first up, what are the goals here? Well, as we're all aware, neuromorphic computing lends well to low power edge applications due to its event-driven nature. This makes them ideal for resource-constrained deployment environments, but adapting to changes in real time can be a challenge. For example, accounting for weather changes, force changes, or imprecise sensor readings can all impact the performance of our target application. Therefore, we wanted to design a system that can perform real-time evolutions of SNNs deployed at the edge and showcase it on a real-world application. So this endeavor consists of three main parts. First is to design a software framework that can train these networks and account for environmental changes. Second is to design a simulator for our target application. In our case, it's dual fuel engine control. And lastly is to design a hardware platform that can load networks, process networks, and interact with the target application. With that, let's first tackle the software framework or neuromorphic optimization using dynamic evolutionary systems or nodes. This framework is responsible for training SNNs in an online fashion that can dynamically adjust the training to account for environmental changes. It's also designed to be general purpose and applicable to various different applications, with the main processes and their interactions shown in the following diagram here. We first have the coordinator process, which is responsible for communicating information between the other processes, as well as keeping track of the best networks. Next, the eons process is responsible for training these networks using the application simulator and an evolutionary algorithm titled eons. These networks are then sent to the sim scheduler for evaluation using simulated and/or hardware neuroprocessors. The real-world interface, like the name suggests, interfaces the nodes framework to the actual deployment environment. In our case, it's the engine control unit of the diesel engine shown here in light blue. And lastly, we have the sim modifier, which takes real-world data and uses it to optimize the simulation parameters, which we call sim knobs, to better represent the real world during training. And I'll go into more details into each of these processes in the upcoming slides. So coming back to the coordinator, again, this process is responsible for communicating information between the other processes, but it also keeps track of the best networks in a data structure that we call the leaderboard. The leaderboard stores the top performing SNNs based on sim knobs, which are basically hyperparameters of the target application simulator used during training. These sim knobs are meant to encapsulate the real world and account for environmental changes. For example, certain combinations of sim knobs can represent changes in weather, changes in forces, sensor readings, and other factors that can impact the target application. The leaderboard can then retrieve and deploy these networks based on these sim knobs, which allows the system to adapt to environmental changes by pulling from a list of networks trained on different scenarios. This is accomplished by first binning the sim knob search space, where each bin is represented by a network with the best fitness score within that respective bin. Next, we create a search radius around our target sim knobs and retrieve the network with the best fitness score within that radius. And this network is meant to represent our target sim knobs. And this is demonstrated by the figure here on the right, where the orange point is the target sim knobs, the black points are the best networks in their respective bins, and the red region is the search radius. Moving on, we next have the eons process. Again, this process is responsible for training networks using an evolutionary algorithm titled eons, or evolutionary optimization for neuromorphic systems. This algorithm begins by first creating an initial population of random networks. These networks are then evaluated and ranked using the application simulator, as well as its corresponding fitness function. The top performers are then selected to act as parents to produce the next generation through a series of reproduction steps. The first of these steps is crossover, where traits of the parent networks called genomes are combined together to produce a child network. This child network can then undergo a mutation process, which introduces random changes to its genome to further diversify the population. This process is then repeated for some number of generations, with the idea being that the last generation will outperform its predecessors. And the reason that we chose an evolutionary approach for this is that it tends to produce smaller networks with fewer neurons and synapses, making it easier to fit onto the physical hardware. It also tends to produce networks with recurrence, which is better suited for time series and control applications. And lastly, the fitness function structure allows us to optimize for various different constraints and objectives simultaneously. However, the framework can be easily modified to support additional learning algorithms, and we plan to explore this element in the future. The networks trained in the EONS process are then sent to the sim scheduler for evaluation. The goal of this process is to offload the compute-heavy component of EONS, which is processing the networks and then calculating the fitness score. This is accomplished by first queuing up the population of networks and then evaluating them using simulated and/or hardware neuroprocessors. Better speedups can be achieved when using hardware neuroprocessors to act as accelerators, but we can still use simulated ones when none are available. Regardless, once the networks are loaded onto the neuroprocessors, simulator instances are created for the target application with the appropriate SimNob configuration. The input observations from the simulator are then encoded into spikes, which then propagate throughout the network. The output spikes are then decoded into usable actions, which can then be applied back to the simulator. The new input observations are fed back into the network while the reward is calculated using the fitness function. So this process is repeated for some number of time steps, where the average reward is acting as the fitness score for its respective network. Finally, the network, its fitness score, and the corresponding SimNobs are all packaged together and sent to the coordinator to be stored within the leaderboard. With that, we can now move on to the real-world interface. Again, this process is responsible for communicating the nodes framework to the actual deployment environment. This involves interfacing with the various hardware components that comprises the overall system. And for us, this includes the FPGA, which is housing the neuroprocessors that are running the SNNs, as well as the ECU of the diesel engine. This process is also responsible for requesting and deploying networks from the leaderboard when the current network running on hardware is performing poorly. Simultaneously, the real-world data gathered from the hardware components are processed and then sent to the sim modifier, which I'll talk about next. And here we have the actual control box or ECU that is controlling the diesel engine, and our hardware and software systems are connected to this component to allow for that real-time control. And the last element of the nodes framework is the simulation modifier. This process is what allows the system to adapt to environmental changes, to adapt to the deployment environment by modifying these SimNobs to account for these changes during training. And this is accomplished by utilizing the real-world data gathered from the deployment environment, where a subset of these observations are set as target observations. These target observations are then replicated by a series of simulator instances that are using the active SNN running on the hardware. The simulated observations are then compared against the target observations using mean squared error, which in turn is used by Bayesian optimization to converge to a series of SimNobs which best minimizes this loss. And this approach essentially allows us to model the environmental changes occurring within the deployment environment. Finally, the SimNobs or the new SimNobs are shared across the nodes framework to ensure that new networks are being trained using the most up-to-date simulators. So to summarize, first, EONS is training networks using SimNobs representing the current deployment environment. These networks are then evaluated using the sim scheduler, then sent to the coordinator to be stored within the leaderboard. The networks that are best suited for the current deployment environment are then selected to be run on the physical hardware. Meanwhile, the sim modifier is attempting to discover SimNobs, which best represents the current deployment environment. And if better SimNobs are discovered, they're then used to update the simulators for EONS training. This scheme essentially allows us to set simulation parameters which we feel would be impacted by outside factors, and then narrow down on these hyperparameters during training to ensure that new networks are being trained for the current environment. Eventually, we would have a suite of networks trained on different scenarios that we can easily swap between as the environment changes to allow for that real-time dynamic control. With that, we can now move on to the hardware setup. The hardware component of this project is titled Firebox, and it consists of a Raspberry Pi 5, Beagle vFire single board computer, and the engine ECU. The Raspberry Pi hosts the Nodes framework as well as the application simulators, and the Beagle vFire board is responsible for real-time processing as well as the communication tasks. It also supports an FPGA fabric where 2 instances of the micro-Caspian neural processor are implemented, and these neural processors were developed at ORNL to act as an easy-to-use neuromorphic solution for size, weight, and power-constrained applications. We also utilized a CAN controller to allow communication between the real-time processor and the ECU. This allows network outputs to be decoded into usable spikes, which are then into usable actions rather, and then applied to the engine via the CAN line. Additionally, we also created a simulated setup where the CAN messages are sent to the engine simulator running on the Pi when we don't have access to the physical engine. And this point will come up later when I go over the results. So a key aspect of this dynamic real-time system is being able to seamlessly transition between networks and avoid periods of time where the application isn't being driven by network outputs. To accomplish this, we utilize the 2 micro-Caspian neural processors that I mentioned earlier, where one of them is set as the active neural processor communicating with the ECU, while the other is inactive and waiting for networks to be loaded onto it. A dispatcher thread is responsible for taking the new the new networks and loading them onto the idle neural processor, and then setting it as the new active neural processor while the other one is deactivated. Simultaneously, a controller thread is responsible for taking the input engine states and encoding them into input spikes, which are then processed by the active neural processor. The output spikes are then decoded into usable actions, again applied to the engine through the CAN controller. Essentially, the swapping mechanism between the active neural processor and inactive one allows for timing constraints to be met, and it provides a seamless interface for the Nodes framework where new networks can be loaded onto the physical hardware as soon as the next engine cycle of the engine. And this is essential for that real-time control. And with that, I would now like to go into more detail on the actual engine control application. Before I begin, I'd like to preface, I'm not an engine expert, so I'll be grossly oversimplifying things. With that being said, I'm sure we're all aware of the current trend of electrification and moving towards electric vehicles to help reduce our carbon footprint. However, certain sectors cannot make this change and will still need to rely on liquid fuels. Some of these examples include marine shipping, locomotives, and heavy-duty transportation, to list a few. Fortunately, alternative fuel sources such as ammonia-based fuels are promising in reducing these carbon emissions, but they still require some amount of diesel to initiate that combustion process. Unfortunately, though, these diesel ammonia-based fuels have wildly different combustion properties than traditional fuels and require adjustment of the control parameters, such as the injection timing, as well as the amount of fuel to inject into the system. Therefore, we wanted to apply a neuromorphic solution to this problem. And this is the first study to use a fully neuromorphic online system to control a dual fuel engine as far as we are aware. And the reason for neuromorphic here is that we hope to capture the cycle-to-cycle variations of the system to make better informed decisions on the amount of fuel to inject, as well as the fuel timing, where traditional controllers simply focus on the average case scenario of these cycles when making these decisions. And here we have a picture of the actual diesel engine that we're trying to control to provide some more context. So in order to develop the system, it is first crucial to create an accurate and robust combustion model. This required extensive data collection of various aspects of the Cummins single-cylinder engine, and this is represented by the figure on the left-hand side here, which showcases the coefficient variability or the combustion variability measured by the coefficient of variation of the indicated mean effective pressure. According to literature, a COV lower than 3% is desirable, and this is represented by the dark blue region within this figure. The solid black line is the optimal crank angle location used during combustion, but you'll notice that it leans towards a higher COV. This means that the controller will need to balance between an optimal combustion location and lower cycle-to-cycle variability, which we'll see these trade-offs when we look at the fitness function. But using this data, we were successfully able to create a physics-based model of the system, and this is represented by the figure on the right here, which compares the blue measured data points to the red simulated data points. And as you can tell, it matches the general trends relatively close, validating our model. So now that we have the combustion model, we can now move on to the fitness function. Again, the fitness function is what's being used by eons to quantify the performance of a potential solution network. It is arguably the most important element of the training process, and it's extremely difficult to design an effective fitness function. It's more of an art than a science and requires a lot of trial and error and expert knowledge. With that being said, we have our fitness function on the right-hand side here, where the first term aims to optimize the combustion timing, while the second term aims to optimize the combustion efficiency. We use an alpha value of 0.02 here as it offered a good trade-off between the two terms. And alpha in this context is simply just a hyperparameter weight. With that, the fitness score is calculated at the end of every single simulation step, where it takes the following as input: the total fuel mass, air mass, and the combustion efficiency. The network then outputs the injection timing, as well as the fuel quantity to be injected into the system. And lastly, to account for sensor inconsistencies or incorrect assumptions about the amount of fuel and air in the system, we use sim knobs, which are meant to represent as multipliers for these parameters to tweak the simulations during training. And these ranges are shown here at the bottom. With that, I would now like to finally discuss the results of our implementation. And first up, we have the results for offline training. Here, we're simply training networks using the EONS algorithm as well as the application simulator. With this approach, we were able to train a series of networks capable of quickly converging to an equilibrium point. And this network shown here demonstrates this by converging to an equilibrium state within 10 engine cycles, and then maintaining the state indefinitely, which showcases its robustness to cycle-to-cycle variations. The yellow nodes are the input neurons, which correspond to the fuel mass, air mass, and the combustion efficiency. The white nodes are the hidden neurons, and the red nodes are the output neurons, which represent the injection timing, as well as the amount of fuel to inject into the system. The black edges are the positive synaptic weights, and the red edges are the negative synaptic weights. And as you can tell from this figure here, it's a jumbled mess. There are random synaptic connections going all over the place. And we like to refer to these networks as hairball networks or spaghetti networks. I'm sure you can guess why. But this structure goes back to the idea of recurrence that I was talking about earlier, as it provides an element of memory to the system, allowing it to better process temporal information. We also performed hyperparameter tuning of several different encoding approaches, including multi-spike encoding, rate encoding, and temporal encoding. Multi-spike encoding uses multiple spikes to encode the value. Rate encoding looks at the spike rate to encode the value. And temporal encoding looks at the spike timing to encode the value. Pretty self-explanatory, right? We also explored using 1, 2, or 4 bins for each of these encoding types. And from this figure here, we can see that all the encoding approaches perform relatively similar to one another, with the goal being a higher reward score. Still, the multi-spike approach with a single bin worked best, and that's what we used for the rest of the study. Unfortunately, we didn't have enough time to do an in-depth review on the decoders, so we simply stuck with rate decoding here. And a big emphasis on the hardware side is being able to quickly load and process networks. So here we have the average inference and loading times of 10 different networks. The inference time begins when we receive the input engine state from the ECU and ends when we decode the output states, or the output spikes. This typically takes around 2 to 4 milliseconds and depends on network parameters as well as network activity. Loading times, on the other hand, depend on the size of the network and usually take around 5 to 30 milliseconds. And although the loading times take significantly longer than the inference times, they're still well below the 50 millisecond deadline used for real-time engine control. And this threshold is showcased by the dotted red line here. Moving on, here we have the results for network performance when controlling the physical engine. This figure here shows the experimental results of a network where network control was enabled after 1,000 cycles, showcased by the orange line here. And as you can tell, the system quickly learns that injecting diesel, shown in red, quickly improves the combustion efficiency. Although the CA50 parameter slightly deviates from its optimal location, it results in increased or improved combustion efficiency, which goes back to the multi-objective trade-offs within the fitness function. Most importantly, though, we can see a noticeable reduction in the cost as soon as the neuromorphic system takes control. And this directly ties into the combustion stability of the system, which is showcased by the COV percentage going below 3% here. And all the networks that we tested on this full system all demonstrated this improvement. Lastly, we have the results for the sim modifier. Note that we didn't have access to the physical engine for these results, so we had to rely on the engine simulator that I mentioned earlier. Our goal was to complete this optimization process within 5 minutes to provide regular updates to the simulator during training, with these sets of results taking approximately 0.4 seconds. And as you can tell from the results here, the multipliers were able to quickly converge to their target values with a deviation of approximately 0.01 and 0.03 for fuel and air mass respectively. This demonstrates that our approach was successful in converging to these target sim knobs. So in conclusion, we were able to successfully create a framework that performs real-time evolution of SNNs while also accounting for environmental changes. We were able to design this framework to be general purpose and applicable to various different applications, and then demonstrated it on a real-world application for dual fuel engine control, where we showcased improved efficiency of the overall system. In terms of future works, we would like to further explore the impact of different fitness functions or cost functions, explore additional learning algorithms, apply the framework to different applications, as well as basically iterate on the overall framework. Lastly, I would like to acknowledge our funding agencies and the rest of the team, which all made this possible. So thanks to them. And that is all I had. Thank you all for your time.